One last useful property of using the Legendre roots as our interpolation points has to do with the orthogonality of the Lagrange bases that result. The product of two m-1 order Lagrange bases can be rearranged in such a way that we have a term that looks something like x minus xi over some particular number, and we have this for potentially each node I. Now, any one particular basis will be, let's say the jth basis will be missing the x minus x jth term. However, if we have a second Lagrange basis of a different particular nodal basis, then this will have this term associated with it, such that we can borrow it into the first bases. So essentially we were able to construct a polynomial that looks something like a product of each of these terms plus some remainder that is a lower order polynomial. So by virtue of having x minus each of the nodes, if we have each of the nodes be equal to the Legendre roots, then this means that this function is, by definition, a Legendre. If all the roots are equal to the Legendre roots, then it's a Legendre. So we can imagine if we have two m-1 order Lagrange bases, we can rearrange such that we get a Legendre of order m and a remainder of order m-2. That remainder polynomial can be expressed as a linear combination of Legendre polynomials all of order less than m, because these form a complete basis for all polynomials. So therefore, each of the components of the remainder polynomial is going to be orthogonal with respect to the order m Legendre. So in other words, if we have the inner product of two Lagrange bases, each of a different order, then the result is 0. If they're the same bases, then we recover the associated quadrature weight for that particular point. So we represent this with the Kronecker product multiplied by our quadrature weight.